Welcome everyone. I am absolutely thrilled you're joining me for this explainer. Today, we're going on a very hands-on journey to demystify basic electrical circuits. We use electricity every single day, right? Literally from the moment we wake up and flick on a light to the phones we constantly carry in our pockets. But how often do we actually stop to think about how it all works? Well, today, we're going to break it all down, step by step, and actually learn how to harness that power ourselves.
So what does it take to harness electricity right there in the palm of your hand? It's a pretty fascinating thought. We're going to take what looks like just a random pile of abstract parts, some wires, a tiny light bulb, maybe a battery, and we're going to transform them into a fully functional, controllable electrical system. By the end of this explainer, you won't just know what a circuit is, you're going to know exactly how to build one.
Okay, let's dive into this. Here's our blueprint for the explainer. 1. Safety first. 2. Meet your components. 3. Building your first circuit. 4. Lighting up an LED. 5. Taking control with switches. And 6. Drawing circuit diagrams. Let's get started.
Section 1. Electrical Safety First. Establishing the ground rules for experimentation. Okay, before we touch a single wire, we absolutely must establish some non-negotiable ground rules. Electricity is incredibly powerful, and it demands our respect. The absolute most critical rule here: never, ever experiment with the power supply at your home or school wall sockets. Even electricity from portable generators is a massive no-go. For our true and safe experimentation, we are strictly using low-voltage portable electric cells or batteries. The kind you pop into a TV remote. Why are we so strict about this? Well, the human body is actually a really good conductor of electricity. If a strong electric current passes through us, it can cause severe injury or even death. This is exactly why you must never touch switches or plugs with wet hands, and why you should avoid handling any equipment if the plastic or rubber insulation is damaged. We've got to keep that electrical flow strictly confined to our wires.
Section 2. Meet your circuit components. The essential cast of characters for our build.
With our safety parameters firmly locked in, let's mentally pick up our pieces. First up is the electric cell. This is our portable source of electrical energy. If you look really closely at the cell, you'll see it has two distinct ends. We call these terminals. One terminal is positive, marked with a little plus sign, and the other is negative, marked with a minus sign. Here's a helpful visual anchor for you. The positive terminal always has that small protruding metal cap, while the negative terminal is just the flat metal disc on the opposite side. Oh, and you'll hear the term battery used a lot. Technically speaking, a battery is actually a combination of two or more of these cells connected together, where the positive terminal of one connects right to the negative terminal of the next.
Next up in our toolkit is the electric lamp. This is your classic incandescent lamp, just like the ones in older torchlights, with wires connected to its base. Inside that little glass bulb is an incredibly thin wire called a filament. That filament is supported by two thicker wires that connect down to the base of the lamp, forming the lamp's two terminals. When electrical energy passes through this whole setup, that tiny filament gets intensely hot, and it glows to produce light. That heat is literally what creates the illumination we're seeing.
Section 3. Building your first circuit. Connecting the pieces to make the current flow.
So we have our energy source and we have our light. Now let's actually walk through the physical construction steps. Step 1, you're going to need some electric wire. The wire is made of a conductive metal, usually copper, and it's wrapped up in an insulator like plastic. You'll need to strip about 1 centimeter of that plastic covering right off the ends to expose the bare metal. Step 2, attach 2 of those wires to the 2 ends of your cell holder, making sure the bare metal firmly touches the contacts. Step 3, take your other 2 wires and attach them to the base terminals of your lamp holder. And finally, step 4, you take the free ends of the wires coming from the cell and connect them directly to the free ends of the wires coming from the lamp.
The crucial point here is what happens the exact moment those final wires touch. Boom, you have just created an electrical circuit. This is a complete, unbroken path that allows electric current to flow. Conventionally, we consider the direction of this current to flow from the positive terminal of the electric cell through the wires and the filament of the lamp all the way back to the negative terminal of the cell. The real magic here is that the lamp is only going to glow when this path is entirely complete. If the filament inside the bulb is broken, what we call a fused bulb, the path breaks and the lamp just stays dark.
Section 4. Lighting up an LED. The modern upgrade with a special twist.
Now let's step into the modern era. The incandescent bulb is great and all, but today, most of our devices use a light-emitting diode or an LED. But here is a massive plot twist. With that old incandescent lamp we just built,
it actually doesn't matter which terminal of the lamp connects to the positive or negative terminal of the cell. You can connect it in literally any direction, and the filament heats up and glows. But an LED, it's a completely different story. It doesn't even have a filament. Instead, it acts like a strict one-way street for electricity. Current can pass through an LED in one direction only. If you hook it up backwards, the circuit is essentially blocked, and there's absolutely no way it's going to light up.
What's really cool is how engineers built a physical cheat code right into the component so you don't get confused. If you look closely at an LED, it has two wires or legs sticking out of the bottom. One is noticeably longer than the other. That longer wire is always your positive terminal, and the shorter wire is always your negative terminal. So to make the LED glow, you have to perfectly match the positive longer wire to the positive side of your battery and the shorter negative wire to the negative side.
Section 5. Taking control with switches. Becoming the gatekeeper of your circuit.
So far, to turn our lamp on or off, we've had to physically tape and untape wires together. Yeah, that's not exactly practical. Enter the switch, a surprisingly simple device that either completes or breaks a circuit on command, and we can build one using just everyday stuff. Imagine making a switch out of two metal drawing pins and a metal safety pin stuck into a piece of cardboard. If you swing the safety pin away from one of the drawing pins, you create a gap of air. Since air is an insulator, the current can't flow across that gap. We call this an open circuit, which is basically the off position. But if you simply rotate that safety pin back so it touches both drawing pins, the metal bridges the gap. The pattern is complete, the circuit is closed, and the lamp instantly glows in the on position. You are literally acting as the gatekeeper, opening and closing a gate for the electrons.
Section 6. Drawing circuit diagrams. Translating physical wires into a universal language.
All right, now that we have a working switched circuit, we're going to transition from our somewhat messy physical build on the table to a neat abstract diagram. Now you might be wondering, why do we even need these diagrams? Well, trying to draw realistic pictures of batteries and safety pins every single time you design a circuit gets incredibly complicated very quickly. So international organizations like the IEC and IEEE created standardized symbols for electrical parts. Basically, this replaces realistic sketches with very simple, uniform shapes. This is an absolutely crucial concept. It means an engineer in Japan can look at a diagram drawn by an engineer in Brazil and understand it instantly. It makes troubleshooting complex systems totally manageable, and the best part, by learning these symbols, you now speak the global language of electronics. So, to translate our physical parts, we use these standard symbols. To draw an electric cell, we definitely don't try to draw a 3D cylinder. We just draw two parallel lines, a longer, thinner line representing the positive terminal, and a shorter, thicker line for the negative terminal. A switch is drawn as a line with a break in it that looks exactly like a tiny little hinge that can swing open for off-F or snap closed for on. But honestly, my favorite is the LED symbol. It perfectly visualizes exactly what we learned earlier. It's an actual triangle pointing in the strict one-way direction that the current is allowed to flow, with little arrows pointing outward to indicate that it emits light. It's just simple, elegant, and perfectly descriptive. And that brings us to the end of our foundational build. We've gone from basic, non-negotiable safety rules to physical wiring. We learned the one-way quirks of LEDs, figured out how to take control using switches, and finally decoded the international language of circuit diagrams. So now that you actually know the language of circuits, what are you going to build next? You've got the tools, you have the knowledge, and you know the safety guidelines. I challenge you to safely take these foundational building blocks out into your own world and explore what you can create. Thank you so much for joining me on this explainer, and keep questioning how the world around you works.